Alrighty, in this video, we're going to talk about measurements and units. When we think about measurement, what we're doing is we're going to be able to relate a physical quantity to a known defined standard somewhere. That's kind of what I mean about measurement. It's a little bit weird and out there, but we're going to try to bring that together. Um, there we go. Uh, unfortunately, I shouldn't say unfortunately, but in working in the science in the United States, we end up working in three different unit systems. Just by the way that the United States is. The metric system is what most of the world uses. The SI system is what science has defined as their units, and the SI system and the metric system are very, very closely related to each other. Um, in the US, we use the imperial system, which is uh, weirder units, but we can deal with that. We're not going to stress too terribly much about that in here. What I want to get us at is what we mean by uh, units and all this stuff. Okay, the SI system is great. They've defined 7 what they call base units. These are for length, mass, time, electric current, temperature, amount of stuff, and luminous intensity. Oh, excuse me. And all other units in the SI system are combinations of these. Okay, and we're going to see some of those derived units later on. Um, this semester, we're not going to do anything with electric current or luminous intensity, but we will see these other ones quite frequently uh, as we do stuff. So we want to get used to these as we do. One of the things that's great about the metric system and the SI system is that we can use these metric prefixes to modify our numbers. So if we're thinking about, and in chemistry, we do this a lot, you think about uh, really large numbers or really small numbers, right? Usually it's a really large number of really small things. Um, you can simplify what your units mean by adding a metric prefix, okay? So what do I mean by that? Well, these are power of 10 multipliers that will help make the numbers make more sense. So let's use kilo, for example, which is right here, okay? Uh, Kilo is a lowercase k, and this means the same thing as you're going to multiply your number by 1,000, right? Our list here says times 10 to the power 3, which is the same idea. Okay. So what that means is we can say if you have 1,000 meters, this is the same thing as 1 kilometer, right? You'll notice on the other slide, the base unit of mass wasn't grams, it's kilograms, and that would mean that 1 kilogram is 1,000 grams. Okay, so, and they work with any of these units. You can put any metric prefix in front of any unit and come up with uh, what they are. So say, for example, you have 2 microseconds. Well, this is 1, 2, that many seconds. And the 2 microseconds system is so much easier to deal with. Okay. This will go hand in hand with something called scientific notation, and there's another video about scientific notation in a little bit, so we can get this under our belt as we do stuff. Okay, so really any of these prefixes can be used for any unit, and we just got to get a handle on what they are. Okay, this is the table from our book. These ones in the red box are ones that I'm going to insist that we know and are able to use frequently, and so anything outside this box you would be given. Sorry, brain freeze. All right. So if we're going to talk about individual things as we go, uh, as far as units go, length. Length is a measure of distance, and meter is our base unit for length. I like the history parts of chemistry as well. So the meter itself has a older definition of 1/10,000th the distance from the equator to the North Pole if you go through Paris, France, which is cool and really esoteric, but that's what they did before nowadays. I think it was 2018 or something like that. They changed the definition to be relative to the speed of light. Uh, it doesn't matter. I don't really care if we know exactly what that is. We just want to know what that meter is length. Okay. There's another unit. This is I believe it's a metric unit. It's not quite an SI unit, and it's falling out of favor, but I still like it. Um, Anders Angstrom is a Swedish physicist, and the unit is named after him. It's called the angstrom. This is not a metric prefix. It's a unit on its own. So you would say 1 angstrom is 10 to the minus 10 meters, or you would say 1 angstrom is 0.1 nanometers. Okay, that's an ugly nanometer. Nanometers, there you go. You can flip that around and say, well, that's 10 angstroms is 1 nanometer. Yeah, okay. We're not going to use angstroms very much, but you might come across some things that talk about wavelengths or atomic distances in terms of angstroms. Mass, this is a big one. Mass uses kilograms. We mentioned this before on the previous slide. There exist many international prototype kilograms or IPKs around the world that are stored. This is a picture of one of them. I think this is the one that's in France, uh, in Paris. It's an iridium platinum alloy that resists reaction and corrosion and all that fun stuff. So it stays 1 kilogram. It's there. It's a reference point for a kilogram. Um, And again, these things have fallen out of favor. And now a kilogram is defined in terms of Planck's constant. And when we get into quantum mechanics stuff, we'll talk about Planck's constant a little bit. But really, the important thing is to remember that mass is measured in kilograms. The other thing we want to get at is the difference between mass and weight. Okay? When you're in physics class, there's a huge difference between mass and weight, right? Mass is the amount of matter. Let me write that down. Amount of matter in something. Okay, so the mass is constant no matter where you are. Okay, the weight depends on gravity. Okay, since the weight depends on gravity, if you're in a different gravitational field, your weight will be different. So this guy that weighs 100, I'm going to assume pounds on Earth, is 16.6 pounds on the moon. Okay, his mass is the same in both places. We're not going to stress about it too terribly much because in chemistry, we're doing all our chemistry on Earth. It's a relatively constant gravitational field, so the mass and the weight are used interchangeably. And we can do that because we're going to use this kind of device. This is a balance. And the balance is calibrated and set up and devised so that it can use the weight to measure the mass. Okay, so we will often use the terms weight and mass interchangeably, which might prickle the hairs on some physicists, but we're not going to stress about it. Okay. Temperature. Temperature is a good one. Sorry, I'm scattered. Okay. Temperature is a good one. Temperature relates to the average kinetic energy of a substance. So this deals with particle motion. We'll talk more about this in a bit. Well, another video. Okay. All we really want to think about here, though, is the faster your particles are moving, the hotter they are, and the more kinetic energy they have. Okay. And since we're just talking about units, we're talking about um, these are three different unit systems, okay? Kelvin is the SI unit, Celsius is the metric unit, and Fahrenheit is the imperial unit, okay? So we're used to things in Fahrenheit. We're not going to use Fahrenheit in class unless I'm going to ask you to convert, and I'll show you how to convert things at some point in another video. Metric is a water-based system, so it was defined so that 0 Celsius is the freezing point and 100 Celsius is the boiling point. Okay. Kelvin and Celsius are directly related to each other because they have defined 0 Kelvin as absolute 0. Okay, so this is defined based off of average kinetic energy. And so absolute 0 means there's no motion of any kind. None of the particles are moving, nothing is happening. Okay, so absolute zero is the coldest number possible. And when we get into the gas work towards the end of the course, we can show you where absolute zero comes from and what that actually means. Okay. So we'll use Kelvin a lot in terms of calculations. We'll use Celsius a lot for measuring stuff, and we won't use Fahrenheit at all in terms of data, but we might use it for some interesting conversion math problems. Other thing I want you to notice, Fahrenheit and Celsius are both degrees. So this is degrees Fahrenheit and degrees Celsius. Kelvin itself is just a capital K. Okay. And I'm going to try not to harp too terribly much, but I want you to be really careful between a lowercase k and a capital K, because these are going to mean different things throughout all of Gen Chem 1 and Gen Chem 2. And so you'll see this again and again. Okay. Volume. Volume, this is our first derived unit. We'll have another, well, probably see lots of derived units throughout the course. Volume is the amount of space that something occupies. Okay. And this is a derived unit because we can use base units to come up with it. So we can say our volume is the length times the width times the height. Since our SI unit is meters, this comes out to be meters times meters times meters, which is meters cubed. So this is the SI unit of volume, is a cubic meter. In terms of chemistry, this is ridiculous because 1 meter cubed is 264.2 gallons. Okay, we're not going to do any reactions or anything on the scale of 264 gallons. Okay, we're just not. So chemistry often uses a unit called the liter. Okay, the liter, this is a capital L liter. Okay, and this is SI is a meter cubed. A liter is a decimeter cubed. So just for a reference from our metric prefixes, 1 decimeter is 1/10 of a meter. Okay. So if you can imagine a cube that is 10 centimeters on a side, each side. Okay. The volume of that cube is 1 liter. Made up in this cube, there's 1,000 little cubes, and those little cubes are 1 centimeter cubed. Okay. So we can put our metric prefixes to use here again. 1 liter is 1,000 milliliters. 1 liter is also 1,000 centimeters cubed. So what this means is 1 milliliter must be 1 centimeter cubed. Okay. And again, this is what our metric prefix is meaning, right? 1 milliliter is 10 to the minus 3 liters, or 0.001 liters. These are things we have to know. Along with the metric prefixes, we got to know these guys here too. Okay. I believe that's all I've got. When we're thinking about converting with, and we're going to get a video or two about converting things, but when we're thinking about converting weird US units and stuff, well, I will give you those conversion factors. But just so we can put this kind of in a way we're thinking of, you know, we often buy sodas in 2 liter bottles, so we kind of have a general concept of what a liter is. But 946 milliliters is a quart. Okay, so that's almost a whole liter is a quart. So you can kind of think that way through it. Okay, I believe that's it for this. Okay, and I'll see you later.